I'm going to draw a couple pictures here which are going to kind of at least review for us what we've done over the last week. And then we're going to make a transition from those two pictures to a different looking picture which will introduce the new topic that we're going to start today and focus on for the next couple of days. We're going to call this object number one. We're going to give it a mass of 30 kilograms, and we're going to give it a velocity of 10 meters per second. Doesn't really matter what the numbers are here because we're not going to actually calculate anything with it, but got numbers for it just for argument's sake. Object number two, it's going to be sitting at rest here before the collision. V is equal to 0 meters per second, and we'll make its mass 20 kilograms. These two objects, for whatever reason, are going to stick together after they collide. In other words, maybe they have Velcro stuck to them or some kind of sticky paint or glue or something stuck to them so that these two objects are going to stick together after the collision. They're going to go off as one object after the collision. We know how to analyze this problem, right? We've done this many times. Not with these numbers, not with two spheres or whatever they are, but we've done this general problem where we have two objects colliding, sticking together many times. We would analyze it every time by saying Pi is equal to Pf. M1 V1I plus, say M2 V2I, but we know that it's 0, right? Because it's at rest, equals MVF, M being the total mass. Right? Does that make sense? Usually what we would do in this case is solve for the final velocity. We could do that by plugging in our numbers and getting the final velocity. We just won't right now just to save a little bit of time. You could, though. And we could pretty easily. You guys okay with me so far? You with me so far? All right. Let's take a look at another one then. Let's say this time that object number one is at rest. It's still 30 kilograms. But this time it's not moving. This time object two is moving downwards. It's still got a mass of 20 kilograms, but this time its velocity is 8.0 meters per second. For whatever reason, these two objects stick together when they hit each other. The glue, the Velcro, the whatever, the masking tape, they stick together. How do we analyze this one? Well, once again, we're going to say Pi is equal to Pf, right? We've done this a million times as well. In fact, this problem, this second problem, is effectively the same as the first problem, right? One's where you have object number one moving and object two is at rest. The other one we have object two moving, one's at rest. But really, we tackle it the same way. 0 momentum this time for object number one because it's at rest, plus M2 V2I equals MVF. Agree? We turn around and we solve for VF. We can do that. Plug in our numbers and get a value for VF. Not that hard. Solve that problem many times. Does everybody agree that we could solve both of these problems if we wanted to in probably about 2 minutes? All right, good. Let me give you a third one. This time, we're going to say object number one, which has a mass of 30 kilograms, has a velocity, once again, of 10 meters per second to the right. But this time, object number two, which has a mass of 20 kilograms, is also going to have a velocity, again, of 8 meters per second downward. So this time, they're both moving. None of them are at rest. Neither of them are at rest. They're going to collide right here at this point, 90 degrees to both of them. They will stick together for whatever reason, the Velcro, the masking tape, the glue, whatever it is, and they're going to head off as one object. They're going to head off down here somewhere, right? You probably make that prediction, right? You know in the first case, they're both going to go to the right after the collision, if they hit straight on, that is. The second case, they're both going to go down. In the third case, they're going to go down and to the right if they go off as one object. My question now is, how do we analyze this green problem? Problem number 3, we'll call it. Do we know how to deal with this? Well, the answer is yes, we do know how to deal with this. Even though we've never solved a problem that quite looks like this, we know how to deal with this. Because even though we've never solved a problem that looks exactly like this, we have solved this problem before. Because this problem that you see there, problem number 3, the green one, is just this problem number 1 and this problem number 2 combined. Here's what I want you to do every time you see a problem involving 2 axes, 2 dimensions, an x and a y. That's exactly what we got here, right? An x-axis and a y-axis, and we've got motion on both of those axes. Every single time you see that. Listen, this doesn't apply if it's just problem number 1 or it's just problem number 2, because we've only got one axis here and one axis here. But as soon as we have both of those axes in the same problem, you need to do this. Break it up into an x component and a y component. Right? This is our x-axis, this is our y-axis. We've got motion on both of those axes as opposed to just the x-axis and just the y-axis. We've got motion on both of them. So break it up into x and y every single time you're dealing with momentum or any other vector, and you've got 2 axes. By the way, just as a quick little aside, if for whatever reason we're dealing with kinetic energy right now with 2 axes, we wouldn't break it up into x and y. Why not? Why would we not break it up for kinetic energy? Yep. Kinetic energy is a scalar. Right? There is no direction associated with it, so there is no x and there is no y if you're dealing with kinetic energy or something else that's a scalar. Right? Clearly, a momentum's a vector. Okay, if there is 2 dimensions involved, we've got to include both dimensions. X and y. All right, so how do we analyze the x component? Good news. We already have. That's the x component. How do we analyze the y component? Good news. We already have. Do exactly the same thing for this as we did over here, and exactly the same thing for this as we did over here. Okay, including the zeros. Including the zeros. When you're analyzing the x component, what I want you to do is pretend there is no y component. Pretend you've got this problem. If we pretend there is no y component for the x analysis here, then how fast is object number 2 moving? If there is no y component, how fast is object 2 moving? It isn't. It's only moving on the y-axis. So if we're analyzing only the x, there is no x motion here. So we'd still say 0 for object number 2. Okay, analyzing the y component, how much of object number 1 is on the y-axis? It's moving this way, right? Moving to the right. How much of it's on the y-axis? None. So if we're analyzing just the y, then this would still be 0. It would look exactly like this. Now, you're going to end up solving for a VF, 2 VFs this time. VF for the x component, VF for the y component. Last thing I'm going to say before I flip the page and have you write down a couple sentences of notes here. Think back to physics 20. What would you do with this at this point? Because we're not quite finished. We're almost finished, but not quite. What would you do with it at this point? Yeah. You'd add them together. So if we got 10 here, let's say we got 3 here. I don't know what it works out to be, but probably not going to be 3. But let's pretend we got 3 there. And let's pretend we got 4 there, even negative 4 there. We'd add them together. 3 plus negative 4 is negative 1. Is that right? Well, you're on the right track, but you didn't quite finish it off. Chantal? You make the triangle, right? We got a 3. Let me make this page bigger here. We got a 3 to the right. We got a 4 that is, negative 4 is downward. This dotted line is what we want here, right? And how are we going to find that? Alex? The Pythagorean Theorem, right. So you're going to say 3 squared plus 4 squared. Why did I pick 3 and 4 as numbers? Easy. The calculation is easy, right? Because I know 3 squared plus 4 squared, square root of that is 5. Probably not going to be quite that easy on a real question. We'd also want to find the angle because the resultant velocity is a vector. We'd use the tan function to find the angle, right? The inverse tan of opposite over adjacent. Does that ring a bell from Physics 20? So what have we done today? Anything new? No. We did a little review of Physics 20, stuff that you already did last year. Listen, this is September Physics 20. Like, this is early Physics 20. What else did we do? We did an x-axis analysis. We've done that for the last week. A y-axis analysis. We've done that for the last week as well. So we did this, which we did already, this, which we did already, and this, which we did a year ago. That's it. Nothing new at all today. It's just putting 3 things together that we've already done. All right? Okay, I'm going to flip the page, give you a couple minutes to write down a little bit of notes on this just to refresh your memory in words as opposed to just pictures. When analyzing a collision or explosion, not of explosion, collision or explosion in 2 dimensions, we want to break it up into 2 separate problems, the x and the y. Remember, the x component is this, and the y component is this. You always want x and y. Always want x and y if you're dealing with momentum and 2 dimensions. Don't ever try to take a shortcut and skip the x and y. Ever. Y. When you're analyzing the x component, of course you're going to ignore anything y. Anything y is just, what number should we assign to anything on the y-axis here? 0. When you're analyzing the y component, you're going to ignore, not ignote. You're going to ignore anything on the x-axis. So anything on the x-axis should be assigned a value of 0. Doesn't exist if it's on the x-axis. Finally, once you've done that, you're going to recombine them by drawing a right-angled vector diagram. It might look something like this. Using the Pythagorean Theorem to find the hypotenuse, and then using a little bit of trigonometry, normally it would be the tan function, the inverse tan of opposite over adjacent, to find the angle, the direction. We need both because velocity is a vector, so is momentum. So let's take a look at a problem here, okay? Page 492. It says a 90-kilogram quarterback is moving at 7 meters per second at 270 degrees, tackled by a 110-kilogram linebacker at 0 degrees. What's the velocity of the center of mass of the combination of the 2 players immediately after impact? All right, there's a few things that confuse me in this problem. First of all, the whole 0 degrees, 270 degrees thing confuses me a little bit. Second of all, the whole center of mass of the combination of the 2 players immediately after impact. Both of those things I think are a little bit confusing. Let's address, first of all, the angles, the 270 and the 0 degrees. Okay, it's a little bit of a confusing thing for you guys because you're not that familiar with that system of notation of describing angles. We did a little bit in Physics 20 because that's what your textbook likes to use. The good news is your diploma exam won't use that notation. I'm going to show you what it means right now, just because we need to in order to go through this problem. But it's not something you're going to have to lose any sleep over in the upcoming months here. This on an XY axis would be 0 degrees. If we keep going counterclockwise, this would be 90 degrees. If we keep going counterclockwise, this would be 180 degrees. Keep going counterclockwise, this would be 270 degrees. Keep going clockwise, this would be 0 degrees or 360, right? So what we've got here in this problem is one football player, a quarterback, we'll call him object number 1, is moving downward at 270. His mass is 90 kilograms, and his velocity is 7.0 meters per second downward. But we got another guy that's 110 kilograms that's moving at 0 degrees. 0 degrees is to the right. So he's going to be moving this way. to the right. His mass is 110 kilograms, and his velocity is 8.0 meters per second. What's the center, what's the direction, the velocity of the center of mass of these players after the collision? What do we mean by center of mass? Center of mass is like an average. It's like an average of where the mass is. Okay, the center of mass of a perfect sphere is right in the middle of that sphere. The center of mass of a hammer is closer to the heavier end of the hammer. Center of mass is where we can consider the mass to be concentrated. If I take, you guys remember projectile motion from physics 20. If I take a rock that's uniform, a uniform sphere, and I throw that rock at an angle, it's going to follow a perfect, what's the shape of that path? It's a perfect parabola, yes, a perfect parabola. If I take a hammer and I throw it at the same angle, then the hammer will not take a perfect parabola. But the center of mass of the hammer will take a perfect parabola. The average of the mass will make a perfect parabola. So at one moment, the hammer might be like this. Another moment, the hammer might be like this. Another moment, the hammer might be like this. Another moment, the hammer might be like this. Right? The hammer's rotating all over the place. But the center of mass of the hammer, the average of the mass of the hammer, is always following that parabola. A center of mass is the average, or where we can consider the mass to be concentrated. So what we're saying in this question is, look, the two players may go off as separate objects, but there's a center of mass, an average mass of those two players that would go off in one direction. So what we're going to do is essentially pretend they go off as one object. Where would it go if it went off as one object? And it will go down and to the right. If we have east, or we have momentum to the right, then we have to have momentum to the right afterwards. If we have momentum downwards before the collision, then we have to have momentum downwards after the collision. We have to have momentum down and to the right. That makes sense? So what comes next? Usually when we see a question, right, we're saying, all right, what's the concept? Is there anything that's with the red pen? Is there anything that kind of stands out to us? Is there anything that we kind of know, but not really givens? Anything that we know about the concept? Now we're going to kind of look at even something else. Now we're going to, whenever we're dealing with momentum or a vector, we have to look at whether it's a one-dimensional problem or a two-dimensional problem. Okay, this is two-dimensional. If you look at that question, that fourth question, basically, that we can ask ourselves now, is it two-dimensional? Then answer yes to that, then you got to break it up into x and y every time. Here's the x component. Pi equals Pf. We're going to say M1 V1I plus M2 V2I equals MVF. Even though they don't stick together, because we're finding the velocity of the center of mass, it's like they stick together. Plug in some numbers. What's M1? Quick, what's M1? Yep. 90 kilograms. Good. M1 is 90 kilograms. What's V1I? Quick. Nope. 0. 0. Why? Why is it 0? Yep. Good. Anything on the y-axis we're ignoring, right? We're pretending it's nothing because we're only dealing with the x-axis here. Now, M2 is 110 kilograms and V2I is 8 meters per second. It's on the x-axis, so we have to include that. The combined mass, well, that's still going to be 200 kilograms, we're still going to include the 90 kilograms here because after the collision, there is at least some x motion of that object, right? That 90 kilogram object is going to go x and y after the collision. So it's important to include that now. VF is what we're solving for here. 110 times 8 is 880. 880 divided by 200, I think, is 4.4 meters per second. Is that our answer? Final answer? Nope. That's the x component of our final answer. That would be this. That would be the x component of that resultant vector there. Okay, let's do the y component now. Let's say pi is equal to pf. Let's say, because we get two objects here, m1 v1i plus m2 v2i equals, they stick together afterwards, mvf. Or at least we're pretending they stick together. M1, what is it? What's M1? It's 90 kilograms. Good. M1 is 90 kilograms. That's V1I. 7 meters per second? Who says 7? Nope. But you're close. Yep. Oh, your hand was up? -7. Why -7? Yeah, because it's downwards. What's M2? 110. What's V2I? Yeah, 0. Because we're now dealing with the y-axis, not the x-axis. So anything on the x-axis doesn't count anymore. The combined mass is 200 kilograms because there is some x motion of both of them after the collision. Solve for VF here. 90 times 7 is -630 divided by 200, I think is -3.15 meters per second. Now what do we do with them? Let's combine them now. Let's say 4.4 to the right, 3.15 downwards. Notice I dropped the negative on the 3.15. It doesn't matter. You can put it in, but you don't need to now because the arrow is showing the direction for me. You got to show direction. Over here, the negative showed it. Over here, the arrow is showing it. The resultant velocity, or the resultant vector, is right there. And the angle is right there. We're going to solve for V by doing the Pythagorean Theorem. Remember, a squared plus b squared equals c squared? Like this is all physics 20 at this point, right? C would be equal to the square root of a squared plus b squared. And theta would be equal to the inverse tan of opposite over adjacent. Let's have a look at this on our calculator. We're going to say 4.4 squared plus 3.15 squared. Let's equals and then square root it all. 5.4 at an angle of, say, the inverse tan function of opposite 3.15 over adjacent 4.4. 36 degrees. Is that good? Yep. All right, let's have a look at these two questions, please, that appear on page 592. Just a reminder, okay, just a reminder, we got a few things that we look at every single time we see a question. Okay, one, what's the concept? Conservation of momentum, obviously. Okay, is there anything that we should circle with a red pen? Well, look, we got 90 and 180. 90 is this way, 180 is this way. Well, it's not really a red pen thing, but kind of comes to one of our other questions is there two dimensions? The answer is clearly yes, there's two dimensions. So whenever there's two dimensions like this or like this, like question number 2, we got to do what? We have to do x and y. Okay, don't ever skip that when you have two dimensions like that. All right, let's get at those questions, and I'll take a walk around and give you a hand if you need help with it, okay? You guys feel like you're okay with those two questions? Let's take a look at one more example here. This one's on page 485. It says, The 0.6 kilogram fireworks bundle is at rest just before it explodes into 3 fragments. So this is an explosion, not a collision. That's okay. We still do conservation of momentum for explosions as well as collisions. So it's at rest at this point right here. It's got a mass of 0.60 kilograms and a velocity of 0 meters per second. But after the collision, or our explosion, I should say, we get 3 pieces. One of them, I'm going to erase this actually, because in the end, if it's at rest, it doesn't really matter, right? The momentum is 0, right? So it doesn't really matter if I have that number written down. After the explosion takes place, we have fragment A going to the west. Okay, that's going to be, I'm going to call it fragment 1, actually. I don't like using letters for some reason. Doesn't matter, though. If you want to call it piece A, go ahead. It's got a velocity of 19.2 meters per, 14.6 meters per second. And it's got a mass of 0.20 kilograms. We got another piece, piece B, or piece 2, as I'm going to call it, 19.2 meters per second to the south. And we got another piece, its mass is 0.18 kilograms. We got another piece, piece C, or I'm going to call it piece 3, that's going to go somewhere. We want to know where. What's your prediction? Where do you think the third piece is going to go here? What's the total momentum of this system before? 0. What's the total momentum of this system after? 0. If we have momentum to the left after the collision, the explosion, we have to have momentum to the right. If we have momentum down, we have to have momentum up. So the momentum of the third piece is going to be up here somewhere, up and to the right. Don't know exactly where, but somewhere up there. We want to find out how fast it's moving. Do we know what it's, how heavy it is? How heavy is it, Alex? Good. Its mass is 0.22 kilograms because it's what's left of the 0.6 kilogram fireworks bundle. All right, there we go. Conservation of momentum. It's an explosion. There's 2 dimensions involved. There's x and y involved. So let's do that. Let's do the x and y component. Pi equals Pf. The initial momentum, x component, 0. Final momentum, m1 v1f plus m2 v2f plus m3 v3f. Just like Alex was saying, though, here we could call that Pf as opposed to m3 v3f. We're going to solve for v3f there. We're going to do the same thing for the y component. 0 is equal to m1 v1f plus m2 v2f, m3 v3f. Solve for v3f. Just remember, for the x component, this guy is 0. For the y component, this guy is 0. Is that any different than the questions you've been doing? No, not at all. Except the initial momentum is 0. And I want you to finish up the last set of questions if you haven't finished them up already. And then in addition to that, I want you to work on page 495. Practice problems that go with that. I think there's 2 of them as well. All right? That's it for today, guys.